The next property of the transpose we are going to prove is this property that the transpose of a product of a certain scalar k and matrix A is just equal to the product of the same scalar k and that already transpose of A. So in short, this means that if we have this expression, you can simply take out the scalar quantity and they're just of the same result if we're going to multiply the transpose or multiply it first before getting the transpose. Of course, for this to be true, we are going to let k be a scalar. Okay? So that we can use that in our proof later. At the same time, and matrix A would be a generalized form of a matrix because this property does not only hold true for a 2 by 2, 2 by 3, or even just a square matrix, other form of matrices. This should be true for all. In short, if our matrix A is an m by n matrix, we could have this representation. M meaning the number of rows and n will be the number of columns. So for this, we can use this representation for matrix A. Let us use this entries. You have A11, A12, A13 until A1n. That's the first row. Our first column would be A11, A21, A31 until AM1. That's why it's called M by N. M, number of rows, n number of columns. This is 1n. So as we complete this, you have A22, A23 dot 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 A2n here, A32, A33 dot 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 A3n. You have AM2, AM3 until AMn. Okay, this will be our matrix and it is k scalar. So we're going to show that from here we can reach this portion here. Now let us try first the result of k scalar k times matrix A because the left hand side allows us to use its transpose. So we need to have this form first. Okay, so the product of k, that means you have here k, we use a scalar k. Okay, and then you have your entries here, A11, A12, A13 dot 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 A1n, A21, A22, sorry for that, A23, A2n, A31, A32, A33 to A3n, and then your last row, AM1, AM2, dot 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 AM3, dot 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 AMn. Since k is right identified as scalar, you can multiply this to each of the component of matrix A. Again, each of the components. So this would mean this is now equal to, when you multiply scalar k, ka11, ka12, ka13 dot 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 ka1n. That's for the first column. Then we have here ka21, ka22, ka23 dot 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 ka2n. You have ka31, ka32, ka33 dot 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 ka3n. And here you have ka m1, ka m2, ka m3 dot 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 ka mn. This is the result of multiplying your k, scalar k, to your a. Now this is again ka, but the first, the left hand side is the transpose of this. So we need to show its transpose. To save some space, of course, let us have it here, the transpose of this. When you have A as matrix which is defined as m by n, its transpose is where you interchange the rows and columns. So you're expecting a matrix here which is n by m. Okay, n by m matrix. Okay, with this, we are going to have here this one here. As we interchange, this would be our first row, a column here. The first row would be our first column. So you have here k a11. This would be k a12, k a13 until k A1N. This one here. We interchange them. Okay? Next, you will have here K. Your second column would be your second, second row would become your second column. K, A21, K, A22, K, A23, dot, 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 K, A2N. Okay. Next, this one here, KA31, KA32, KA33, dot, 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 to KA3N. And your last column for your transpose should be the last row of your original matrix. So you have KAM1, KAM2, KAM3, and then until KAMN. Okay. Now from here, notice that take note of our goal, we need to reach this portion. You can see here that all the components of this matrix has scalar k. In short, we can factor out k. Once you factor out k, what remains in our matrix would be these components only. A11, A21, A31 until AM1. You will have A12, A22, A32 until AM2. Then A13, A23, A33 until AM3. And here you have A1N, A2N, sorry for my handwriting, A3N, and AMN. Okay. Now, this is now the new form, and we have established already the K. Earlier, it was part of the transpose as shown here. Now, from this point, we were able to take out K, which is now close to this goal. We just need to show what type of matrix is this. Notice A11, A21, A31, AM1, the components of the first row, was originally the column of your matrix A. And your original row of your matrix A11, A12, A13 A1N is now the first column. This would mean that this matrix is just equal to the transpose of A. And with this, you will have K here. So from this form, which is just the transpose of the matrix of the result of K, scalar K and matrix A, we have this. We have now shown that the transpose of Ka, where K is a scalar and A is matrix, is equal to K, the scalar K, times the transpose of matrix A. This is the intended part of our transpose. Property of this property. Now from here, since we have established to be true in our future reference, in our future dealings with matrices involving transpose, if you have something like this in any value, negative, positive, fraction, or irrational numbers, you can simply take it out and it's just the same as the product of the transpose itself of A and that same scalar quantity. This is Properties, Laws, and Theorems. Please subscribe now.